Here is a combined summary of the 2 pages. Research on self-supervised goal-conditioned reinforcement learning, GCRL, has the potential to transform reinforcement learning, similar to the breakthroughs seen in other areas of machine learning. However, current self-supervised GCRL methods have not achieved similar success due to a lack of data from slow environments and a lack of stable algorithms. This paper addresses these issues by releasing a high-performance codebase and benchmark, JAX GCRL, for self-supervised GCRL, enabling researchers to train agents for millions of environment steps in minutes on a single GPU. The key to this performance is a combination of GPU-accelerated environments and a stable, batched version of the contrastive reinforcement learning algorithm, based on an InfoNCE objective, that effectively makes use of this increased data throughput. This approach provides a foundation for future research in self-supervised GCRL, enabling researchers to quickly iterate on new ideas and evaluate them in a diverse set of challenging environments. The paper focuses on goal-conditioned algorithms, which aim to use unsupervised interactions to learn a policy for reaching different goals. Prior work has proposed several algorithms for self-supervised RL, but they have not yet provided the same sort of foundational building block as self-supervised learning in other domains. The key barrier to realizing effective self-supervised RL algorithms is scale, algorithms and implementations that can collect extraordinarily large quantities of data and stably learn from that data. This paper removes this barrier by providing extremely fast simulators that are tightly integrated with simple and scalable self-supervised RL algorithms. The framework is broadly accessible, avoiding the complexity of distributed training and not requiring more than a single GPU. The paper combines insights from self-supervised RL with recent advances in GPU-accelerated simulation, enabling users to collect data at almost 200,000 steps per second on a single 24 GB GPU. The paper also builds upon recent work on contrastive RL, which uses temporal contrastive learning to learn a value function. The suite of tasks for evaluating self-supervised RL agents is not only blazing fast but also stress tests the exploration and long-horizon reasoning capabilities of RL policies. The key contribution of this work is a codebase that provides a highly stable implementation of self-supervised RL that is tightly integrated with a GPU-accelerated suite of environments. On a single GPU, an experiment with 10 million environment steps lasts only around 10 minutes, which is more than 10 times faster than in the original CRL codebase. Here is a combined summary of pages 3 and 4 of the research paper. The proposed codebase aims to make reinforcement learning, RL, more accessible and reproducible by providing a unified framework for goal-conditioned reinforcement learning, GCRL, and hardware-accelerated environments. This will enable researchers to run experiments quickly and efficiently, even with limited computational resources. The codebase builds upon recent advances in GCRL, which combines scalable contrastive learning algorithms with hardware-accelerated environments to enable fast and stable training of self-supervised RL agents. GCRL is a special case of multitask RL, where an agent learns to reach arbitrary goals in an environment defined by goal states. The GCRL setting augments a Markov decision process, MDP, with a potential reward function for each possible goal state in the MDP. Recent work has shown that representations of goals can be imbued with additional structure to enable capabilities such as language grounding, compositionality, and planning. The paper also discusses the importance of accelerating deep RL, which has only recently become practical for many tasks due to improvements in hardware support. Distributed training and GPU-accelerated environments have enabled RL algorithms to scale across hundreds of GPUs. Self-supervised RL and intrinsic motivation have enabled key breakthroughs in language modeling and computer vision, and have been used in multi-agent games and goal-reaching agents. The proposed benchmark and implementation aim to address the bottleneck of environment interactions in self-supervised RL by providing a fast and scalable implementation and algorithm for contrastive, self-supervised RL on a benchmark of diverse tasks. The RL community has recently started to pay greater attention to how RL research is conducted, reported, and evaluated, and a key issue is a lack of reliable and efficient benchmarks. The paper then delves into the details of self-supervision through goal-conditioned reinforcement learning, where an agent interacts with a controlled Markov process to reach arbitrary goals. The goal-conditioned policy receives both the current observation of the environment and a goal observation, and the objective is to maximize the likelihood of reaching the goal. The paper derives the discounted state visitation distribution and the Q function of the policy, and formulates the overall objective as a maximization problem. Finally, the paper discusses contrastive representations for goal reaching, where the objective is to learn a policy that maximizes the likelihood of reaching goals. This is achieved through a contrastive learning algorithm that scales with GPU acceleration to enable fast and stable training. Here is a combined summary of pages 5 and 6 of the research paper. The paper proposes a goal-reaching policy learning approach, where the critic is learned by maximizing a contrastive loss function. The critic is defined as an energy function, and the loss function is a function of the matrix containing the critic values. The policy is learned using a DDPG-style policy extraction loss, where the policy is parameterized as PED, A, S, G. The overall objectives are to minimize the contrastive loss and policy loss. The paper also introduces a new implementation of state-based self-supervised reinforcement learning algorithms, which leverages the power of GPU-accelerated simulators to reduce the time required for data collection and training. This implementation mitigates the bottleneck of former self-supervised RL implementations, which was limited by CPU-based data collection and data migration between CPU and GPU. The new implementation enables researchers to run extensive experiments in a fraction of the time previously needed. The paper releases a new suite of GPU-accelerated environments and algorithms for studying goal-conditioned RL, called JAX-GCRL. The environments range from simple 2D manipulation tasks to complex, exploration-oriented tasks, and are implemented in JAX, enabling parallel trajectory collection from thousands of environment instances. The benchmark includes 8 diverse continuous control environments, including Reacher, Half-Cheetah, and Pusher, which require spatial navigation, spatial layout understanding, and object manipulation through agent interaction. The paper evaluates the speedup of the proposed implementation using the basic goal-conditioned contrastive RL method, and reports a 22-fold speedup in the ANT environment. The implementation uses only one CPU thread and has low RAM usage, as all operations, including those on the replay buffer, are computed on the GPU. The paper discusses the implementation and evaluation of contrastive reinforcement learning, CRL, in various simulated environments. It presents the success rates for each environment, including ANT, Half-Cheetah, Pusher Hard, and Humanoid, demonstrating the effectiveness of CRL in high-dimensional tasks. The authors also explore different energy functions and contrastive losses, such as info-NCE, flat-NCE, and Monte Carlo forward-backward unsupervised loss, to understand their impact on performance. Additionally, they investigate the effects of architecture scaling and layer normalization on the CRL algorithm. The experiments use a suite of simulated environments with specific parameters for network updates, batch size, discount factor, and replay buffer size. The paper aims to establish a strong baseline for CRL in these environments through a thorough examination of well-known methods. The research paper discusses the influence of design choices on learning performance in goal-conditioned environments. It compares various energy functions and contrastive losses to establish the most effective algorithm. For energy functions, L1, L2, and dot product outperform cosine similarity, with the dot product showing the best results. In contrastive losses, info-NCE-derived objectives, such as symmetric info-NCE, perform well, with the originally used NCE binary objective being the worst. The paper also examines the impact of scaling the architecture by increasing the depth and width of neural networks, finding that adding layer normalization improves performance even in deep and wide architectures. This research aims to establish a baseline for goal-conditioned environments and identify the most effective design choices for future work. The paper proposes a fast benchmark and baseline for goal-conditioned reinforcement learning, focusing on self-supervised methods. It explores the performance of different network architectures and contrastive losses. The authors observe that only a subset of design choices performs well in scaling contrastive RL. They also introduce a new benchmark that enables rapid study of design choices for state-based CRL. The paper concludes by highlighting the potential of self-supervised RL methods to open new learning algorithms and emphasizes the need for accelerating and democratizing this research. Future work should relax assumptions common in practical settings and examine the offline setting. The summary begins by discussing the JAX library, which enables composable transformations of Python plus NumPy programs. It then moves on to OpenAI's GYM, a toolkit for developing and testing reinforcement learning algorithms. The paper also explores the concept of human alignment of large language models through online preference optimization. The section on action and goal-oriented reinforcement learning highlights the importance of understanding the relationship between actions and goals. The discussion on contrastive learning as goal-conditioned reinforcement learning emphasizes the significance of goal-conditioned policies. The paper also touches on the topic of planning and inference through the use of variational causal reasoning. The summary concludes by mentioning the need for scalable and efficient reinforcement learning methods, highlighting the importance of sample-efficient automated deep reinforcement learning. In the realm of reinforcement learning, a multitude of research papers have been published, focusing on various aspects such as unsupervised skill discovery, goal-conditioned reinforcement learning, and the use of language models for robotic control. This summary will encapsulate the key findings and methodologies presented in these studies. Firstly, the concept of empowerment, as introduced by Klubin et al. 56, is a universal agent-centric measure of control that can be used to guide the exploration of an environment. It is defined as the maximum number of possible outcomes an agent can produce in its environment. This concept has been applied in various settings, including robotic navigation, 60, and language models, 82. Unsupervised skill discovery is another area of research that has garnered significant attention. Papers by Laskin et al. 59, Park et al. 79, and Park et al. 81. All explore different approaches to this problem, utilizing techniques like contrastive learning, Lipschitz constraints, and metric-aware abstraction to learn skills without explicit rewards. Goal-conditioned reinforcement learning, on the other hand, aims to train agents to achieve specific goals. Studies by Myers et al. 74, Park et al. 80, and Myers et al. 73 demonstrate how language models can be leveraged to represent goals and guide the agent's behavior. These methods often involve learning transferable visual models, 92, and utilizing hindsight policy gradients, 84, for efficient exploration and learning. Furthermore, the integration of language models in reinforcement learning has shown promising results. Papers by Radford et al. 82, Sardana et al. 88, and Rajani et al. 83 illustrate the potential of using language models for common-sense reasoning, scaling data trained language models, and leveraging language models for robotic control. Lastly, hardware-accelerated parallel game simulators for reinforcement learning, as discussed in Koyamada et al. 77, are crucial for efficient training of reinforcement learning models. Similarly, the use of GPU-based physics simulation for robot learning, as explored in Makovichuk et al. 85, can significantly enhance the speed and efficiency of the learning process. In conclusion, these papers collectively contribute to the advancement of reinforcement learning by introducing novel methodologies, leveraging language models, and optimizing computational efficiency. They demonstrate the potential for unsupervised skill discovery, goal-conditioned reinforcement learning, and the integration of language models in reinforcement learning, paving the way for further research in these areas. This research paper presents a comprehensive study on reinforcement learning, focusing on the optimization of goal-reaching reinforcement learning algorithms. The authors provide an extensive list of relevant references in the field, covering various aspects of reinforcement learning, including deep reinforcement learning, intrinsic motivation, and goal-conditioned reinforcement learning. The paper then delves into the experimental details, presenting a thorough analysis of the speed-up comparison across various numbers of parallel environments. The experiments involved running the algorithm for 10 million environment steps, with different numbers of parallel actors for data collection. The results show a significant variation in success rates associated with different numbers of parallel actors, suggesting that increased diversity in the data supplied to the replay buffer leads to more varied experiences for each policy update. Furthermore, the authors investigate the speedup in the Ant-U maze environment, demonstrating the effectiveness of their novel repository in providing a substantial speedup. They attribute the differences in asymptotic performance to the disparities in physical backends used for the Ant-U maze environment between the repositories, with Brax still under active development. The authors propose that future versions of the repository will likely exhibit reduced performance discrepancies. They also highlight the interesting observation that the variation in success rates is worthy of further investigation, suggesting that the increased diversity of data supplied to the replay buffer may lead to more varied experiences for each policy update. Overall, this paper provides a thorough examination of reinforcement learning algorithms, highlighting the importance of optimizing goal-reaching reinforcement learning methods and the potential benefits of using parallel environments to accelerate the learning process. The paper discusses the evaluation of different energy functions in various environments, highlighting the variability in performance across environments. Figure 12 shows the success rate and time near goal for different energy functions in Ant, Ant Soccer, Ant Big Maze, Ant-U maze, and Pusher environments. It is observed that no single energy function performs well in all environments. The paper also provides technical details on environment parameters and benchmark parameters used for the experiments. Table 1 lists the environment details, including goal distance, termination, and Brax pipeline. Table 2 presents the hyperparameters used for benchmarking, such as num_time steps, max_replay_size, and policy_LR. The paper further discusses the contrastive RL method, including the loss function and the policy extraction loss. The hyperparameter alpha controls the rate of counterfactual goal learning, and the authors suggest using alpha equals 0 for better performance.